Today I am going to teach you the fundamental theorem of arithmetic. So before we go to that, I would like to give you few concepts. All the numbers are divided into two types. In this case I am using prime numbers and composite numbers. Prime numbers which have no factors except 1 and itself. Composite numbers which are not prime numbers. That means composite numbers are having more factors than 1 and itself. I will give you an example also. For example, 6 is equal to a composite number. The reason is 6 having the factors 1 is a factor, 2 is a factor, 3 is a factor, 6 is a factor. 6 has a 1, 2, 3, 4 factors. Every number is divisible. You take 7 for example. 7, only 1 is a factor. Again 7 is a factor. That means 1 and itself. Therefore here the 7 we call it as a prime and 6 we call it as a composite number. So these two based on the factors only. So now here you should understand how to make the factors, right? So factor is very simple. 1 is a factor of 7 because 7 divisible by 1, 7 divided by 1 is equal to 0. If you divide, 2 is a factor of 6, 2 is a factor of 6, that means if you divide 6 with 2, you will be getting remainder 0. So if remainder is 0, then we call 2 is a factor of 6. This is what is a factor you must have learned in lower classes. So here you should understand what is a prime number, what is a composite number, what is a factor, etc. Then only you can easily understand the fundamental theorem of arithmetic. Now here every composite number can be factorized because it has more factors. Then only you will call that number as a composite number. Okay, more than 2, if any number is having factors, then we call that. So every composite number we can factorize it. We can factorize in terms of prime numbers. That means all these factors. For example, you take 6. 2 is a prime number, 3 is a prime number, and 6, of course, these two we should eliminate it. So now 6 you can write a 2 into 3. So 6 is a product of 2 and 3. 2 is one factor, 3 is one factor. 2 is a prime number, 3 is a prime number. Every composite number can be expressed as a product of prime numbers. We can call these two as prime factors also. Let us take a big example, 36. So how to find out 36? How to express 36 as a product of prime factors? You divide this 36 with a prime number starting with 2. 2 18s are 36. Again 2 is one prime factor. Again 2. You take 2 9s are. Now 2 is not divisible. 9 is not divisible by 2. 3 3s are. So now 36 you can write like 2 into 2 into 3 into 3. That means 36 we have written, we have expressed as a product of prime factors. So this product of prime factors, this is unique. You do in any way. Sometimes you will divide 36 with 3 in the beginning. So whatever the product, you write in the ascending order of the numbers. Now already this is in the ascending order of the. So now these two, only 2 factors. So this 2 into 2 will become 2 square and 3 into 3 square. You do the prime factorization of 36 in any way, in any manner, and this will be unique. Maybe order of the numbers are different. Okay. So you do in any way, whatever the method you follow, and this factorization is unique. This is what is a fundamental theorem of arithmetic. Every composite number can be expressed as a product of prime factors in a unique way. Use the fundamental theorem of arithmetic in a problem. 4 to the power of n. This is a number where n is a natural number, integer. This, whatever the natural number is, this, there will be two possibilities. It will be ending with 0 and do not ending or cannot ending with 0. That means, for example, in the place of n you write 3. So 4 to the power of 3 is 4 into 4 into 4, which is equal to 64. So 64 is not ending with 0. This is what is the meaning of ending with 0 or ending, do not end with 0. Okay. So now, and for any number n, this do not end with 0. This is what we have to prove. Suppose if this number ending with 0, that means the last digit should be 0. Let us say this is x, whatever. Okay, this last digit, this is what does it mean? If it is ending with 0, that means it looks like. Then it has unique prime factorization. Unique prime factorization. So in this unique prime factorization, 1 2 will be there and 1 5 will be there. Then only 2 into 5 is 0. Okay. So these 2 factor and 5 factor will give this 0. If this has both 2 and 5 as factors, if this is having 2 and 5 are the factors, then this number is ending with 0. So now we have to prove that this do not have 2 and 5. Both should be there. If only 2 is there, no problem. If only 5 is there, then also there is no problem. So 2 and 5 only will give the last digit 0. Let us do factorization. 4 to the power of n, 2 into 2 whole to the power of n. So 2 square whole to the power of n. So the only factor is 2 and there is no 5. There is no 5. 5 is not a factor. Okay. Therefore, this do not end with 0. Because it has only 2 as one factor, no 5 factor, therefore it will not end with 0. So if 5 is also a factor, then it will be ending with 0. So this is one of the application of fundamental theorem of arithmetic. So you can have one more question. 6 to the power of n. So factors of 6 are 2 into 3. So there are only 2 factors, 2 and 3 prime factors. No 5. Even this also do not end with 0. You take 8 to the power of n. So 2 into 2 into 2 to the power of n. There is only one factor, 2 is repeating, so only one factor 2. There is no 5. Therefore, even this also do not end with 0. This is how you have to decide whether this given number is ending with 0 or not. So everybody has to learn prime factorization because it is mainly involved in the fundamental theorem of arithmetic. So you should know how to express a composite number as a product of prime factors, that I have explained in my previous lesson. Now using the same thing, find HCF of, let us say, 10 and 25. Find HCF of 10 and 25 by prime factorization method. So every composite number can be expressed in a unique way. The factorization is unique. 10. How to write 10? Like very simple, 2 into 5. So 2 into 5. 25 is 5 into 5 or 5 to the power of 2. Prime factorization. Now HCF, the full form of HCF is highest common factor. So now here 5 to the power of 1 and here 2 to the power of 1. If there is no power, we can say, right? So now here 5 to the power of 1 and 5 to the power of 2. The highest common factor is equal to 5 to the power of 1. That means 5. The least power of the prime factor. Okay. So HCF is 5. Then in the same way, I will do LCM also. LCM. No need to do again the prime factorization because already we have done. So you write this HCF 5 to the power of 1 into, here what is left? 2 is left. And here out of 5 square, 5 came here and 5 is there. So 5 into 2 to the power of 1 is 2, 10, 5 is 50. So 50 is the LCM. So this is also we are doing using the prime factorization. Now you just multiply HCF into LCM. HCF is 5 into 50 is equal to 250. You multiply these two numbers, 10 into 25, 250. If these numbers, as if you are assuming it as A and B, this is A and this is B, HCF, let us write H only. H into L is equal to A into B. You can have a direct statement like this. H into L, HCF into LCM is equal to the product of two numbers. I hope you have understood. Based on this, we can do few more problems. Let us try to understand theorem number 1.2. It says like this: let P be a prime number, and if P divides A square, then P divides A, where A is a positive integer, right? Actually nothing is there to understand, but we have to prove it. So let us prove it. We have to apply the fundamental theorem of arithmetic. So it is the prime factorization is unique. Let us say A is equal to P1 into P2 into P3 and so on Pn. A is a composite number, positive integer. So A is the product of P1, P2, P3. That means P1, P2, P3 are up to Pn are the factors. They need not be the same, right? They may be different also, but A is equal to, let A is equal to P1 into P2 into P3 into Pn. Then what happened to A square? And what happened? This entire thing, P1 into P2 into P3 to Pn into, because A square is A into A. So again P1 into P2 into P3 and so on Pn. So finally we get P1 square into P2 square, P3 square and so on Pn square. So this is A square is equal to this. So what is given here? P divides A square. That implies what happens? P is a factor of A square. P is a factor of A square. A square is equal to this. That implies what happens? P is a factor of P is one of the factor, because if P is a factor of A square, then P will be there in this. P is a factor of or one of the factor of P1 square, P2 square and so on Pn. So that implies P is a factor of, if I can say P1 into P2 into P3 up to Pn. I can write like this also. So that implies P divides, this entire thing is nothing but A. P divides A. Okay. In this it looks funny, but this is how we have to prove it. I hope you have understood. Do it 2 or 3, 4 times.